Welcome to our NPTEL course set Power Quality Improvement Technique. Today we are going to discuss about multipulse converter. Now we have discussed already 12 pulse converter, we left with the just 18 pulse converter, and thereafter we mainly discuss the PWM 3 phase PWM rectifier. Now let us come to the 18 pulse converter. So, ultimately this 18 same way this concept can be extended to the 24 pulse converter. So, you have a constant current source due to the highly inductive load, and there is a source inductance, and generally you have to give some amount of the inductance to be connected before to smooth out this the THD part of it. So, it will generally make this entity more continuous. So, essentially for the in this case you can find that Ls for, let us take the entity B. So, in that case you will find that the power the THD for B for full load, it is close to 2.5, 2.3, and for half of the load, this line and you can get close to 4%. So, it is some extent acceptable, and for this applications for where for this rectification where you are feeding highly inductive load. But problem, why is a problem? Problem in this case are all these multipulse. We require to understand that there are, let us close this discussion first. For alpha equal to 60 degree, again this is a C curve, and you get the THD close to 7% for the full load, and if alpha equal to 20 degree, then you can get this curve around 6%, and of course, alpha if it is 20 degree, because you got a displacement power factor, you get a THD close to 4 to 5%, and power factor is just does not change much, but for the C, for the lowest triggering angle, I mean highest triggering angle, alpha equal to 40 degree. So, you get close to 0.78, and for B you get close to 0.9293, and for A you get very close to 0.9598, something like that. So, this is the overall 18 pulse converter. Same concept can be extended to the 24 pulse converter, and see that what is the benefit of this. And one of the benefit is that in case of the C, that you can see that this curve is almost same. So, there is no such benefit can be attended by connecting the extra converter, but B you can see that it is close to the same. So, in terms of the power quality, you can see there is not much difference of the 18 pulse and the 24 pulse converter. But here there is a advantage. You can see that A goes to less than 4% for alpha 20 degree for full load. Similarly, this is B, it is 40%, and C, that is 60%. Same way THD alpha THD A equal to alpha equal to 0, that is not the case, generally we prefer. Otherwise, you can see that this is the variations, the same variation which you will find in case of the series load, almost very close to that variation you will get this kind of series inductive load. Now, what are the major drawback of this multipulse converter? One of the major drawbacks of the multipulse converter that since this you are feeding a DC load, and if there is a mismatch of the triggering angle of this converter, then there will be a mismatch of the DC component in the primary, and also this leads to the saturation of the transformer. One problem is that, so we require to ensure that once you have to see that whether you have any DC component in any of or traces of the DC component in any of the current part of your circuit. So, accordingly you require to adjust the triggering angle and you require to eliminate the DC portion of it, otherwise you are going to saturate the transformer core. That is the major corrective action you require to take with a regular interval of time by proper monitoring of it, and thus you can operate it for the longer durations, otherwise it will cause unnecessary heating up of the transformer and ultimately it will go into the saturation. And apart from that, all those multipulse converter are a bulky solutions. You want to have a solutions with the transformer, and thus solutions are quite bulky, and it is applicable for the mostly these are the thyristerized drives. Mostly you will be applying these drives for driving your vehicle in case of your for the power rating in the range of the MVA. For the lower rating, we generally prefer for the up to 3 kilowatt you have a single phase system. We have discussed the problem of the single phase system, THD, power quality, other issues. Now, the 3 phase system in the level of the MVA, you will go for this multipulse converter, and there, since the power handling capability of thyristors is quite large and it can handle this power, so you will have this entity to be fit from thyristors. But if you have, let us say, a power rating of around 100 kilowatt, then we shall go for the 3 phase rectifier, that is 3 phase PWM rectifier we will use. And so, we will have this is the something we will discuss, that AC to DC conversion, improve power factor, reduction of the input current THD. So, one of the application of this is called the Vienna topology, but it consisting of the huge number of switches, and these are the 3 utilities, and ultimately it fed to this bidirectional switches. This essentially are the bidirectional switches. If you can find it out, you can find. So, current can flow from this point to this point, and if you want this switch to be on, then current can go this point to this point, then can pass on this point and can go this way. So, there is a multiple connections possible depending on the logics, and ultimately this is the way, but it is quite complicated in operations and you require large number of diodes. These are all power diodes, and ultimately while current flows, it account 2 diode and 1 switch losses unnecessarily. So, 2 diode losses will be around, it is not 0.7 volt diode, these are all high power diode, and for this reason this drop will be quite maybe double of the 0.7, maybe 1.5 volt. So, you got a 3 volt, there will be a switch that also gives you around 2 volt sometime if it is high rating IGBT, then 5 volt drop will be there and if it is carrying a 100 ampere of current. So, this each of the set will give you a 500 watt losses, you know. So, it is equivalent to run a 500 watt motor. So, since you are not using it as a room heater, so no purpose of having this kind of configurations, but this is one of the primitive topology was developed by the switches, and this is called the Vienna topology and is controllable active rectifier, and also bidirectional action sometime was also possible with a little change in the circuit, and it gives you a controllable output voltage, high PF and low THD. You can see that this is the voltages and this is the current IIBIC, and is a high power factor and the THD low high efficiency, but efficiency required to be challenged this term because of this high, it has a high diode drop, high conduction loss, but switching losses is little lower. And but this is one of the issues that control is quite complicated, and what's EMI for the passive AC to DC conversion than this your multi-pulse or converter. And for this reason we try to find one solutions by your 3 phase, that is power factor correction topology. Not only power factor, it is also reduces the THD, and it is for the 3 phase. For the low power rating it will be 2 level, and if you go higher level it can go to higher level. And this is the voltage. I will show you the practical current and voltages. I have worked on it, for this reason I can show some practical results. And this is the IS, and you can see that this kind of ripple switching has to be done in that pattern. So, 3 phase PWM rectifier topology is a controllable active power rectifier once you flow power from this point to this point. Of course, in case of the regenerative braking or some other action, in case of the microgate kind of applications where you have a storage, you can feed back this power to the AC side to DC side, and it has high power factor, low THD and controllable power factor. Generally this point can be connected with the 3 phase inverter, and it can have a efficiency up to 95%, and the control is little complicated, not so complicated, and also there is a problem of EMI EMC because of the switching of the device. You can see that I have shown the waveform. Once the current goes to this is the DC action, current goes to grid to DC, and you can send power back to the grid if you have a storage element of the capacitor. Then voltage and current will be 180 degree out of phase, and you can also have lagging or leading power factor, that is also you can do it. Then you of course you are correcting the power factor of the system, since you have made leading power factor in this case as I have shown. So, it may compensate the lagging power factor from other parts. So, it can act as a power factor corrector or STATCOM kind of applications. And this is its multi-level version. I have shown the 3 phase 3 level diode clamp inverter for handling higher power capability. You can of course go for multi-level depending on its power rating. So, but switch counts becomes more, and this is one of the simplest multi-level inverter. 3 level PWM rectifier topology is a controllable active rectifier, controllable output voltage, and bus balance is possible, high power factor and low THD, controllable power factor also possible, because here you can see that you can change the voltage and current angle. Not only you are feeding a unity power factor, if you want to have a you want to have a want to compensate the negative var, you can inject the positive var by proper switching. The control is more complicated, because we shall discussed already the MLI, multi-level inverter. So, there is a 3 kind of multi-level inverter we have discussed, that is, one is your direct clamp inverter for the 3 level and its switching pattern. Already please refer to that lecture, and another is that it has a complicated switching technique, and thus it makes more complicated. The controller thus is more complicated, and you can have also a cascade option also for the, and also for the flying capacitor topology. So, how does it work? So, this is the single line diagram. Generally, this is for the battery charging application. You will find we want that charge our battery for the 0 unity power factor. Then this will be an inductor, and this is the IGBT, and that can be operated as high as, for the lower power rating, as high as 20 kilohertz. I will show little data on it. The PWM rectifier can be equivalent figure above, and we can get this equation E equal to this grid voltage equal to VL plus B, and we, assuming that there is no losses in AC to DC conversion, thus we can say I AC into VAC equal to I DC into VDC. This is the balance of power, and ultimately you can have a different kind of model. So, when vector A stresses from the A to B in the above figure, the converter works in a rectifier mode. When the V at the B, then we can get the higher power factor, then we can get the highest power factor. Same way in C, we can give voltage back, and ultimately in this case I, you can see that I is leading, in this case I can be lagging, and you can see that I is 180 degree phase shift. That means you are sending back the power to the grid. Same way here I, here VL and V are, this gives you the lagging power factor, and you have I in a direction of the E. So, various combinations are possible for this phase rectifier, PWM rectifier, and thus different function can be accomplished with this rectifier. Now, this is the principle of operation of the PWM inverter. I just go by switch. You can see that this is IR, and this Q2 is closed. So, current will flow through it, and assume that all the upper switch is open. So, you can have the logic is this upper switch is, this lower switch is closed, and this is closed, and this is closed. So, this is essentially a state in the space vector modulation is as 0 0 0. So, that is what we have considered, and in that case what happen, this will gives you the boost mode of operation. You can see that depending on the direction of the current, because IA plus IB plus IC should be equal to 0, and here current will, assuming that this IA entering will enter and will go back through this diode D4 and D6. So, this is the, and ultimately what happens, since you have shorted the voltage, since you have shorted, so there will be a ramp on of the current. For example, for phase R, when Q2 is on, then inductor current will rise, the current flow from R phase then go through the essentially it is go through the diode from Q4 and the Q4 body diode at least, but if you have a IGBT, generally it is not body diode, you have to, the manufacturers physically points this anti-parallel diode at least to get the S and T phase. Generally this is a German abbreviations A, B, C. So, B will be equal to S and C will be equal to T. So, that is what the convention we have followed. So, you can write as B or C phase, then the energy will store into the inductor. Similarly, now let us consider that those switch was closed and you have opened that switch, then what will happen? And these two switches are closed. Since you have closed this switch, ultimately this IR will flow through the body diode of Q1 or this external anti-parallel diode you have connected and will boost up the voltage, and ultimately it will flow through these lower switches and back. So, this is the way of the operation of this converter. Now, these are practical circuits of this multipulse, this PWM converter. This is a static bypass, and generally you will have an inductor and we will have a choke, and you require to design the choke. So, that will be depending on essentially what is the value of the switching frequency for the continuous conduction mode, all those issues required to be taken care of. So, from there you can design the value of the inductor. This is the something we shall discuss in the next class. What should be the value of this inductor and how you will select this choke. So, thereafter there will be a switch, and this is the I have ordered this board from the Texas Instrument. So, you can also student version may be available from there. So, they used this circuit courtesy to the Texas Instrument. They have used this IGBT, and which has a 1200 volt 10 ampere at 100 degree centigrade, and we are using electrolytic capacitor of 750 by 750 volt, and generally it will be boosting the voltage, and thus once you rectify it, it will goes to the 600 volt for the 440 volt line. So, and you will find that this voltage will be around 700 volt, 750 volt, something like that. And for this reason you will be using to capacitor of the rating of 450 volt, so that 900 volt can be used. Now, these are the calculations, and control all those aspects has to be there. So, this is the value of this. Ultimately you can write it out for the phase R or equivalent to A. So, that is L di dt plus R I equal to R minus U A, where A is the pole voltage of this leg A. Similarly, U A equal to the duty cycle plus into D 1 plus V D C, because if one switch is on. So, from there you can balance. So, this is your equation number 1, L di dt plus I R equal to V R minus D 1 V 0 minus V C. And same method we can write it for the other phases, that is S and T, and ultimately we know that we can get V D C equal to minus 1/3 d 1 plus d 2 plus d 3 V D C, and we can ignore the higher order harmonics, and thus what essentially you get V D C is can be equal to minus V D C from here. This is the constant value of it and this is the variable value of it, and thus this is the control loop you require to control. This is the duty cycle of V 0 and you are giving a feedback through this inductor, and this is your objective function, nothing but an inverter. So, you are controlling this controller, and so into the control loop what you have essentially, you have the inverter, from there you have multiplied with the D 1, the duty cycle is coming, that will be multiplied by V 0, and same way what you essentially get it, you get it divided by your phase voltage V R, and this is your inductor, and thereafter essentially you get I 1, and that makes you the V D C. You require to control this control block of this current control loop. So, essentially for the system of the large capacitor, we can choose the voltage controller by experience, and this system can be chosen like this, and use the above parameter can be built by the Simulink MATLAB, and you can do it by the either of this thing. We generally prefer the Simulink for the sake of the simplicity. I am showing you the Simulink model of this A. So, you can use the controller and the choke, this is the capacitor, whatever you have, and you can have a switching logic based on the S function block, or you can use any other way which you are preferred. So, this will be switching, and I am giving you just for the your interest that this is the DC bus voltage, these are the currents, once it starts it will spikes, thereafter it will stable down. So, this is the VDC and this is the R phase, S phase and T phase, and thereafter the condition direct input for 0 to 0.4 seconds, thereafter condition 2 at 0.04 second steps reference to 700 volt, and condition 3 we got a full load. This is the yellow one, you can see clearly because of the switching there is a ripple, and this one is a phase current, and with that there is a small red portion or the pink line. So, this is a voltage and which has been scaled down by 100 times to show in a same scale. So, this will be your voltage and they are in a same phase, that is what we have simulated. Of course, you can have a phase lead, phase lag, another options are possible. So, this is the phase current, the 3 phase current, and this is the corresponding, the upper one is the phase voltage and lower one is the phase current, and this is some simulation experimental results. This is a current waveform and this is the voltage and current waveform. You can see that they are in a cophasor. Thank you for your attention. This is I just complete the some fundamentals of the PWM rectifier. I shall continue some design of this multipulse converter as well as the design of this PWM inverter in subsequent classes. Thank you so much.